Now, for my grade 10s, for factoring, there's sort of three main types of factoring that you learn. One, you should always look for a common factor first. Two, is if you have a trinomial, then it factors, right, to be something like two binomials. X plus 1 times x plus 3, that's equal to x squared plus 4x plus 3. This is a trinomial, and usually you can factor trinomials. Not always. And then 3 is a type of factoring called difference of squares. That's when you have something like x squared minus 9, and that's x plus 3, x minus 3, when the first ones are squared and the last one is squared, and there's a difference in between. These are the main factoring things that you've had up till now. So when we look at the first one, is there a common factor, something you can take out? Of all of them, no. Is it a trinomial? Yes. So it's probably going to be this. Now, when figuring out what's going to be there, you have to have multiplied, hopefully by now, hundreds of binomials times binomials out together. And hopefully every time you multiply them out, you're looking for a pattern. The pattern you should notice is that the first ones always multiply to get your first one. The last ones always multiply to get your last one. Have you ever noticed that? And then you would still have the outside and the inside, they combine to give you the middle term. And so in English, sometimes we use FOIL to talk about multiplying these out, because the first ones multiply, the outside ones, the inside ones, and the last ones multiply. Now you can use that as your hint, and you use your first ones, I'll color code it the same as I did over there. You can use your first and your last ones as your hint. In this case, my first one isn't the greatest hint, because it's a 6. It could be 2 and 3, or 6 and 1. But one of those has to work. So some people just pick one at random and try and find out if it works or not. Okay? Other people use a few other strategies. For example, I see my last one's a 3. If it's going to work, it has to be 3 and 1. See that that has to be, and it doesn't matter if I write 1 or 3 or 3 and 1 to start with, because you could rearrange these however. So those have to be 3 and 1. Now, when I look at my first one, should I choose 6 and 1 or 2 and 3? If I chose 2 and 3, there's a possibility that my outside, right, here's my outside, here's my inside, I need to make 7. Can you see that if I put the 3 here and the 2 there, my inside is 9, my outside is 2. That would make 7 if it was 9 minus 2. So I need to make this minus, so that it's minus 2, this plus, so that it's plus 9. And then when I'm done, I do a quick check. Does 2x times 3x give me 6x squared? Do my last ones work? Plus 3 times minus 1, minus 3, yes. Do the outside and inside give me 7? Yes. Second question, is there something in common in all of them? Yes. This time, there's an x. So, I can factor that x out, leaving me with 2x squared minus 3x minus 14. Now inside the brackets, I have a trinomial. So I can think of this is my first one, and this is my last one. And maybe it'll factor. In this case, can you see that the last one has options? It could be 1 and 14 or 2 and 7. But the first one doesn't have options. If it's going to work, it's going to have to be 2x and x. Here's my outside, here's my inside. Can you see two things that multiply to give you 14? So that your outside and inside can add or subtract to give you 3. And you see that if I put, well, 14 and 1 doesn't seem to work anyway. 14 with the 2 gives me 28, and the 1 in the middle, that's not even going to come close. But 7 and 2 is going to work, but it's going to matter where I put the 7. If I put the 7 here, I get 14 and 2, that never makes 3. But if I put the 7 here, and the 2 here, my inside is 7, my outside is 4. I need a minus 3, so I would write minus 7 plus 4. Multiply it out. Do your last ones give you the minus 14? They do. Do your first ones give you 2x squared? And we just checked the outside and the inside. So really what factoring, a lot of what factoring is knowing how to multiply really well. Because you're undoing that. So if your mental math skills are good in multiplying something out, in FOILing, as we often say, you can undo that when you have to factor. And for the last one is not a trinomial. There's nothing in common, but there's a minus sign, and this is a perfect square, and this is a perfect square. So for the last one, to get 49x squared would be 7x and 7x. To get 36y to the 4 would be 6y squared and 6y squared. One will be plus, one will be minus. And when you multiply this out, your first ones give you this. Your last ones give you this. But can you see that the outside and the inside, when you multiply this out, cancel each other out? Because one is plus and one is minus. So technically, the difference of squares is really just trinomial with a 0 in the middle. But we talk about it as something different because it's easy to recognize. And you saw lots of differences of squares in your identities. So next up, I asked you to do synthetic division for the first 3. How did you do? And then I asked you to, it says, plug in 1 into the first equation. Did you get 0? Plug in 3 into the second equation. Did you get 4? And plug in negative 2 into the last equation. Did you get 0? What do they match up with? They match up with the remainder. Do you see that? Why does that work? Well, pretty cool. I gotta change the letters here because I changed this one and this one. I changed this one, which was my green one. This was h of x, and this was my black one. This one was g of x. If you did synthetic division and wrote the division statement, would you agree this is the division statement here? Would you agree the division statement here and the division statement here? Now, when I am figuring out p of 1, well, since p of x is equal to this, I could plug in 1 for x. This is really easy mental math. This is going to be 3 times 1 minus 2 times 1 minus 1. You probably could see that one easily to be 0. I could also plug, since p of x is this as well, I could plug the 1 into here. Can you see easily that the answer is going to be 0 when I plug 1? Because the first factor, 1 minus 1, is 0. 0 times, I don't even have to do the mental math here. I could. 3 times 1 plus 1 is 4. 0 times 4 is 0. Okay? In the second one, this would not be so easy to plug in 3. You'd have to do 3 cubed, 27 times 3, 81. minus 8 times 9, 72, 81 minus 72 minus 3 plus minus 2, and you get 4. Not as easy mental math. But if I wrote the division statement, can you see how easy it would be to plug in 3? This will be 0 times this. Doesn't even matter what that is. This whole thing will be 0. What am I left with? Just the plus 4. Just the remainder. Same thing with this one. If I plug in negative 2, this will all be 0. Is there any remainder? No. And this idea is called the remainder theorem. And we really can see the remainder theorem. Oh, is everybody getting an emergency alert? Okay. It's just a test to make sure. Okay. They're gonna have a lockdown. Let's say whatever class you're in, just stay there for 24 hours and learn as much as possible. See some people's eyes are like, that would be the worst day ever. Oh, it wouldn't be too bad. Okay. So, what we just discovered was something called the remainder theorem. You can put a star beside it at the bottom of page 16. If you're dividing by x minus a, and you plug in that value opposite into the polynomial, you get the remainder. And the reason we saw is if you took the division statement, in the division statement you always have the divisor, x minus a, whatever it is, and if you plugged in a, you would get 0 there. Doesn't matter what the quotient is. 0 times anything is 0. You get just the remainder in the end. And at the bottom of the next page, they have the factor theorem, which is basically the remainder theorem said again. But it says, if you use the remainder theorem and you plug it in and you get 0, then you know something is a factor. So what we're getting to is now we're getting to a method of, I have a way to see if something is a factor or not. If there's no remainder, then it's a factor, then I could factor it. Like we found out in this first example, well, this first example of 3x squared minus 2x minus 1, we found out that x minus 1 was a factor. And we found out that the other one would have to be 3x plus 1. Could you have factored that using our old techniques? Absolutely. But this last one with the 2x to the 4th, if I asked you to factor that, you'd be like, I can't do that. Well, now we've started factoring. We found one factor. Maybe there's more factors. Maybe we can factor it even further. So let's go to example 1. Determine the remainder. Okay? If they're asking for the remainder, you can either do number 1, use the remainder theorem, or number 2, use synthetic division. So someone says, can you find the remainder? You can either use the remainder theorem or use synthetic division. I'll do both, and you can decide on this one which one you think is better. The remainder theorem says, if I'm dividing by, and I'm going to do this, let p of x equal all of that. Yes. So the remainder theorem would say then I should plug in 3 into p of x. If I plug in 3, I would get 2 times 3 to the 4th minus 5 times 3 cubed minus 5 times 3 squared plus 5 times 3. Basically, wherever you have an x, you plug in a 3. And now you just need to evaluate. 3 to the 4 is 81 times 2, 162. 27 times 5 is minus 135. 9 times 5 minus 45. 5 times 3 plus 15 plus 3. Minus 180 plus 180 is 0. A remainder of 0. That's pretty nice. So we know that that's a factor. Okay? In green, I'm going to do the synthetic division. Synthetic division, you would set it up. Are these in the right order? Yes. Is there any missing? No. Opposite sign out in front would be a 3. How do we do synthetic division? Bring the number down, multiply, add, multiply, add, multiply, add, multiply, add. There's my remainder. Which did you like better? Synthetic division? Good. Definitely I think synthetic division is better here. Why? Mental math wise, if we look at multiplying, the biggest multiplication you had to do in synthetic division was 3 times 2. Alright? Yes. You knew that practicing that last night would come in handy, right? In the remainder theorem, you had to do 3 to the 4, which is 3 times 3 times 3 times 3 is 81, then times it by 2 to get 160. That's pretty big. 27 times 5, that's some pretty big multiplication. So the mental math, a little bit harder. What's the biggest you had to add in synthetic division? Ooh, it was the minus 5 plus 6. Was that hard? That's my minus and a plus. Right? That. Right? Minus 5 plus. Right? Over here, you had a lot of adding. Now, depending on how you added it, I noticed that these would be nice to put together to get negative 180, and these would add together to get positive 180. So I did some mental math tricks to make it easier, but definitely the adding was better in synthetic division. Is synthetic division always better? No. Is it most of the time? I would say yes. Synthetic division is good better most of the time. And in addition to that, the synthetic division lets you write the division statement. And we've already started to factor it. We factored p of x with synthetic division. We got our division statement. That's factored. I don't know if it's factored completely. Maybe this could be factored even more. But we've started to factor it. Whereas the remainder theorem just tells you the remainder is 0. And then because it's 0, you could say, oh, because of the factor theorem, that's a factor. But then you would still have to do synthetic division to figure out the division statement. All right, part B. The only time I actually find that the remainder theorem is quick mental math is if you have a really small number here, like 1. X plus 1, x minus 1, remainder theorem, no problem. But with x plus 2, I would probably say, I don't want to do the remainder theorem. I want to do 2, negative 5, 5, 3. I'm dividing by x plus 2, so I'd write a minus 2 out here. Bring it down, multiply, add, multiply, add, multiply, add, and there is a remainder of 45. So synthetic division is often quicker to find the remainder, but sometimes you will need the remainder theorem. There are some questions that require the remainder theorem. So I'd like you to circle 4a, 6a, 7, and 8.